A common misconception in programming is that languages are always either compiled or interpreted. That's not true for several reasons, so in today's video, I want to add some nuance to this. I will explain what these terms mean, how several popular programming languages fit into these categories, and how any of this matters in practice. You have probably heard someone say before that Go is a compiled language or Python is an interpreted language. But what do developers mean when they say this, and is this a useful or even correct way to describe programming languages? I think statements like these are inaccurate at best, and you might be surprised to learn how much more depth there is to them. Saying Python is an interpreted language is a little like saying that airplanes are painted red and run on wheels. Sure, some airlines sport a red logo, and planes also use their wheels during takeoff and landing or when taxiing on the tarmac. You'd probably agree with me though when I say that this would be a gross mischaracterization of what an airplane is. In my mind, there are two major misconceptions at play here. The first misconception is that compilation and interpretation can't coexist and somehow represent opposing concepts. That is absolutely not true. In fact, some of today's most popular programming language implementations for Python, Java, or Ruby, just to name a few, use both interpretation and compilation in some way. So interpretation and compilation often go hand in hand. The second misconception is that whether a language is compiled or interpreted is a property of the language itself. That is also not true. A programming language is just a set of syntactical and grammatical rules. It is up to the particular language implementation whether interpretation, compilation, or a combination of the two should be used to run programs written in that language. This is where these discussions can get really confusing because there's often more than one implementation for a given programming language. Python, for example, has dozens of different implementations. Its canonical implementation is CPython, which is written in C, but there are other implementations that all make different choices about how a Python program should execute. Let's unpack my first point a bit more. Before we can understand how compilation and interpretation can cooperate, we should first nail down what these terms actually mean. Let's start with compilation. There are two aspects of compilation I'd like to clarify here, as they are often misunderstood. First, compiling a program simply means translating it from one language to a different language. However, and this is my second point, this does not always mean we compile source code written in a high-level programming language like Go or Python to machine code designed to run on a CPU. Compilation can also occur between source code and an intermediate format, or an intermediate format and machine code. As we will see in a minute, both may or may not happen when running a Python program, depending on which language implementation you use. Another point we need to understand is that there are two fundamentally different ways in which compilers translate programs. Ahead of time, meaning at build time before we run the program, and just in time, which happens when the program is running. Again, depending on the language implementation, both AOT and JIT compilers may be used to translate a language from source to machine code, often in several consecutive steps. So much about compilation. What does an interpreter do then? Interpretation means executing a program that is not already available as machine code. Unlike a compiler, the interpreter's task is to actually run the program rather than just translate it to another language. This also implies that interpretation can never happen at build time. It requires help of another program, usually a virtual machine of some kind, to process the original program at runtime. However, this does not mean interpreters don't also perform translation. While some interpreters map the syntax tree from the original program directly to functions implemented in a virtual machine, they may also require some form of compilation to happen first. If that sounds confusing, it will become clear in a moment when I show you how all of this works in practice. Let's consider these two simple programs, written in Python on the left and in Go on the right. These programs can't directly run on a CPU. CPUs require programs to be expressed using low-level instruction sets, often referred to as machine language. These instruction sets provide relatively primitive operations such as adding or multiplying numbers, loading values into CPU registers, or execute branching logic by jumping to a different program location. Both programs must therefore use either an interpreter, a compiler, or some combination of these to turn Go and Python syntax into machine code. The steps I'm going to show you in the following examples are specific to particular language implementations. In the case of Python, I strictly refer to CPython, which is the official Python implementation that you would download from python.org. For Go, I refer to the canonical implementation available at go.dev. For simplicity, I will just say Go and Python from now on, but keep that in mind. Let's start with Go. Go uses a fairly traditional way to build programs similar to C and C++. It comes with an AOT compiler that takes a Go program and produces an executable binary containing machine code. This executable can run directly on a CPU, and the instructions embedded in it are an amalgamation of the machine code representation of the original hello.go program, the Go standard library, and the Go runtime. I won't dwell on what these do here, just know that they are an integral part of any executable Go program. The main takeaway is that nothing happens at runtime in terms of interpretation or compilation. Note as well that what ultimately runs on the CPU is your program. There is no need for a virtual machine or additional interpretation. CPython uses a very different approach from Go. The biggest difference is that nothing happens at build time. Instead, you pass your program to the Python executable, which is itself a program written in C. This Python executable has already been AOT compiled to contain all the necessary components to run Python programs as machine code, including a virtual machine. When you tell Python to run hello.py, two things happen at runtime. First, a JIT compiler will translate the Python syntax in hello.py to an intermediate bytecode language. This bytecode can't run on the CPU either, since it's not machine code, but it's a more efficient way for Python to represent and store your program in memory in a platform-independent way. Second, Python will then interpret this bytecode by mapping it to functionality baked into the virtual machine, which provides functions in machine code the CPU understands, such as print this text to the standard output. So you see, Python is not a fully interpreted language. It is both compiled and interpreted, at least when running it with CPython. Note that unlike with Go, it's not your program that runs on CPU, not directly anyway. It's the virtual machine embedded in the CPython executable. The original code from hello.py only exists in memory as a bytecode representation of its former self. Okay, I hope you're still with me. This was admittedly not the simplest example to digest, but it should have demonstrated that compilation and interpretation can indeed go hand in hand, and that there can be various forms of compilation, some of which happen at build time, others at runtime. Let's turn to the second point of confusion then. Using a compiler or interpreter is usually a choice and not something that's strictly tied to programming language design. Take our simple Python program from before. There is absolutely nothing about this program that demands it to be either interpreted or compiled. We've already seen that CPython does both. But that's not the only way to run this code. NuItka is a Python program that can take another Python program like this one here and AOT compile it to machine code. In other words, we've taken the same program but now built and run it much the same way we would build and run a Go program. But that's not all. As of version 3.13, CPython includes another JIT compiler. This Tier 2 compiler takes bytecode that was previously compiled from source code, or Tier 1, and compiles it again to machine code. This makes bytecode interpretation on hot paths of the program unnecessary. The same is true for this Go program. There's nothing about this program that would stop someone from using an interpreter to run it. However, Go is marketed as providing high performance, and at least in part this is accomplished by front-loading any form of program compilation or interpretation. That said, I'm not aware of anyone having implemented a Go interpreter, and I'm not sure why anyone would want to do that either. But that does not mean there is something about Go that demands it to be compiled ahead of time. This is starting to get a little wild, but I really want to drive this point home. So far, all examples for AOT compilation involve compiling source code directly to machine code. Are there AOT compilers that don't compile to machine code? Of course there are. Java, at least the canonical implementation most people will be using, ships with an AOT compiler that compiles Java source code to Java bytecode, not machine code. The Java VM then either interprets bytecode directly at runtime or uses a JIT compiler to produce machine code. There's also an alternative Java distribution called GraalVM, which contains an AOT compiler that produces machine code, allowing your Java program to run directly on CPU. Honestly, if I haven't blown your mind by now, I'm not sure what will. Going back to where we started then, when someone says Go is a compiled language, what they really mean is the official Go distribution includes an AOT compiler that compiles Go programs to machine code. And when someone says Python is an interpreted language, well, then they're just wrong, because likely they are referring to the CPython implementation of the language, which also uses a compiler. A more accurate way to talk about it could be CPython uses a JIT compiler to compile Python programs to bytecode, and an interpreter to translate bytecode to machine code. Please don't say that at a party though, or they're right to kick you out. Before we finish, you may be asking, does any of this matter, or why should I care? I could think of a few reasons, but again, the answer may not be as straightforward as you might like it to be. The first thing to note is that it's usually easier to write programs that are platform independent when not using AOT compilers. The reason is that the onus is on you, the developer, to provide precompiled versions of your program for all platforms you target. For example, if you write software in Go and your audience is spread across various operating systems and CPU architectures, then you must compile your program for each of these individually. End users must then download the appropriate version matching their operating system and CPU architecture. This is not the case when targeting CPython. Because CPython's virtual machine sits between your program and the end user, you only need them to install the CPython version matching their setup once. All you need to do yourself is distribute the source code. This is sometimes called write once, run anywhere. This sounds like a point against AOT compilation. However, a reason to lean away from interpreters and JIT compilers and toward AOT compilers could be performance. As you probably remember, there is a lot going on when CPython runs a program, and this is true for other language interpreters. Anything that can't be front-loaded and happens at runtime will incur additional costs on both CPU and memory. For example, a JIT compiler might start to kick in at a performance-sensitive segment of your program and slow it down. Interpretation and JIT compilation also require more memory. Because the original source code is loaded and processed at runtime, it adds to whatever memory the VM itself already occupies. Memory can also inflate further as parts of the original program are recompiled into either bytecode or machine code. However, modern language interpreters are efficient enough to handle a wide range of applications without breaking a sweat. And the added memory use is often worth the added flexibility. So this shouldn't be a reason to throw the proverbial baby out with the bathwater. The final point I want to mention is debugging and performance profiling. This is a problem that hits close to home since I used to work as a performance engineer on a large Ruby on Rails application. When you run an AOT compiled program, Because it is fully present in the executable in a way the CPU can understand, you can use a wide array of debuggers and profilers to get relatively straightforward answers to questions such as how much memory does the program use, or which function is taking up the largest share of CPU time. Applications running inside a virtual machine like CPython suffer from a split brain problem because there are two programs to consider. First, the one you wrote, and second, the VM itself. Remember that from the perspective of the OS, it's the virtual machine that runs on the CPU, not your program. Your program has become data the VM keeps in memory. If you were to point a CPU profiler at a Python process, all you would see is that the VM is currently busy executing bytecode instructions, but that's not particularly helpful. What we want to know instead is which of our own functions is running, and this requires bespoke tooling. Similarly, memory use can be difficult to track, since two kinds of memory must be considered. The memory your program references, which is managed by the VM, and the memory the VM running your program uses itself, which is what the operating system sees and reports through system monitors. Determining what exactly drives memory growth can therefore be difficult. That's all I have for today. If you find this video useful, please leave me a like and subscribe to my channel. Thank you for watching.